So this is question number 2.1. So by consideration of the cylindrical element control volume as shown below, use the conservation of mass to derive the continuity equation in cylindrical coordinates. So I think this solution is already given in the previous lecture. So but I'm going to explain it in a fast way. So for example, we have a one element here from the polar coordinates. So this is just actually the idea of this one. So this is a cube of, if you have a polar coordinate here. Okay, so this is the idea of this one. Okay, so and then we have a three axis, so which is the axis of radial, and the z-axis, and also the tangent, which is the theta. So we use the idea of continuity equation. So we have this idea, mass flow rate inlet minus mass flow rate outlet is equal to dm dt. So and then we could calculate the mass flow rate here by using this equation, rho AV, which is the V here is the velocity of fluid. So I think you could do this. So m in minus m out. So the detail in the previous lecture notes. So this is the inlet for R axis, and then the outlet for the R axis, and not R axis, the radial axis. So and then we could get we could simplify the value of dr times dr, and then we could have the idea of inlet mass inlet minus mass outlet for radius axis as this one. So and then if we do the Vz, the velocity for the z-axis, we could these terms. So and then this is the mass flow rate inlet minus mass flow rate outlet for the z-axis. For the theta axis, and then we could calculate the mass as this one, and then we substitute in dm over dt, and then we could get the terms here. So we rearrange all the terms according to this equation. So we could have this term. And then to simplify this one, so we divide with d theta dr dz. So and then we could have this one. So again, I would like to advise you, please make sure that every time that you do your calculation using the partial differential form like this one, please make sure that you really understand the symbol that you use, because sometimes in master level we just not use equation to solve problem. Sometimes we will do one method called curve fitting. So we get an equation from all the data distribution that we get from the experimental to create our own equation. So that some kind of curve fitting. And then sometimes you need to eliminate a few terms, depends on the physical meaning of that term. Maybe from the mathematical solution the term exists, but in the real world the term is need to be neglected to make sure that your calculation will be tally with the experimental work. So for example here, so we have the term dr dt here. So from the mathematical point of view, so it just dr over dt, but in the real world dr over dt means the changes of radius in terms of time. So means that if your element is not expanding, means the radius is not expand in time, so means that you need to understand that dr dt is actually 0. So means there are no changes of r regarding to the time. So this is very important, because sometimes if you keep having these terms, so maybe it could make your solution or your result is incorrect. So after we neglecting the terms of dr over dt, so then we could simplify it as this one. So I think we already focused on this in last chapter, in previous chapter. So I think I will stop here.